Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate Let's talk about discontinuity now. So discontinuity is essentially something that is not continuous. Pretty straightforward. On page 84, you're going to have a few pictures here of some examples of discontinuity. So I'm going to go through them quickly here. So the function a, so we have a, b, c, d, e, and f. So a is considered continuous at x equals 0. Okay, so this is a nice continuous function, but they gave us this point to focus on. Now, the function b, or the function in b, would be continuous if we were able to fill this hole. But it's not filled, so we would say this is discontinuous, okay, at 0. The function in c would be continuous if instead of f of 0 being 2, if this point was down here and filled the hole, then it would be. But this is still discontinuous at x equals 0. But it's continuous everywhere else on its domain. The discontinuities in b and c are considered removable. Okay, so each function has a limit as x approaches 0. And we can remove the discontinuity by setting f of 0 equal to the limit. So we can remove the discontinuity, in other words, we can fix the issue if we just redefine how the function is evaluated at 0. Okay, so these are both considered removable discontinuities. Now, let's look at D, E, and F. The discontinuities in D through F of this whole catalog of discontinuities are more serious. So the limit of f of x as x approaches 0 does not exist, and there's no way to improve it by changing f at 0. In other words, we can't fix it. It is not removable. So I'm going to go through some of this, but I want you to look at the pictures as I talk about it. So in D here, the step function, this has what's called a jump discontinuity, because if you think about it, you'd have to jump up to keep going to get on the next level. That's how I always think of it. The one-sided limits exist, but they're totally different. So you can see the limits don't agree, so it's jump discontinuity. Now, the function in this one, if you look at this one now, of 1 over x squared has what's called an infinite discontinuity, because it has that vertical asymptote. And vertical asymptotes, we know how to create the limits off to a positive infinity, which is not a value. So this is an infinite discontinuity. The last one in F here, this one is considered what's called an oscillating discontinuity. So what happens is, as you get closer to 0, the function oscillates from -1 to 1, no matter how close you go. So it goes back and forth between them, and it doesn't actually settle on a particular value. Okay?